Today the second session start with Professor Kumar sir from Anna University, Chennai. I think no need any introduction, Kumar sir. Let us start with the talk, sir.
Okay. Yeah. Thanks to all of you once again for joining in this lecture. Yesterday I was discussing more about the crystal growth processes of various important techniques. Just to have some kind of continuation, I want to highlight a few of the related issues. For example, what are the types of crucibles used, what kind of dopants used, because some questions were there for N-type and P-type. So I'll just try to have a quick review of those aspects, and then we will try to have another aspect of this talk. So I will share one of these slides. Okay, so these are some of the techniques which I spoke about yesterday. Are you able to see these slides?
Yes, sir. We are seeing, sir.
Okay. So you know that I told about Czochralski, then about Bridgman, where the crystal will be grown inside the crucible, whereas in Czochralski we try to pull the crystal out of the crucible. This is the major difference between these two. Here there are some big advantages, like you can grow large size of the order of 600 kilograms, whereas in this it is very difficult to have a container which can hold these 600 kilograms of material. So generally it is about let's say something like 2 to 3 kilograms in Bridgman. Say, for example, I have listed some of the materials which are widely used for various technological applications. Oxides, as I've been telling you, is used as lasers, is used in transducers, is used in scintillator materials like bismuth germanium oxide, and there are several other oxides which are used for various device applications. They are grown either by the crystals from pulling or by the container assisted growth, which is known as Bridgman. It can also be grown by a technique which is known as flux, which is nothing but a high temperature solution growth. It can also be treated by floating zone. It is impossible to grow them for these oxides, but it can be kind of assisted growth can be done in terms of the floating zone. We use various possibilities to assist these growth techniques, like for example, resistance heating or strip heating is used. And once you use this resistance heating or strip heating, you can achieve the relevant temperature. I will show you in the next few slides what are the temperatures which are being used. We can use RF heating, which is radio frequency heating. Generally 450 kilohertz of that order is used. There are also some groups which use lower frequencies. It depends on the coupling coefficient between the heating element, or rather the RF frequency, and the material which is used for growing the as a crystal. Laser assisted heating can also be done, which is generally done for floating zone activity. Electron beam heating can also be done for mostly oxides. Materials which have non-congruent melting point, which means if they have decomposition before the melting point, or if they crystallize or solidify into two different phases, both Czochralski or Bridgman cannot be used. The most commonly used technique is what is called as a flux core technique, and in this resistance heating or any of this heating can be used. For homogeneous doping, which is mostly needed for many of the applications, it is considered that these three techniques are relatively not so comfortable for all dopants. It is not that it is impossible to get this kind of homogeneous doping in Czochralski, but for all type of dopants, it may not be so convenient, whereas a floating zone is convenient for all type of dopants, because the zone thickness or the heating element thickness is very, very small. And if you consider the relative cost of production, these are all relatively high costs of production. whereas this floating zone is considered to be normal in the sense compared to these techniques where there are so many sub-elements like cooling elements and then viewing systems, control systems, etc. Whereas floating zone is not a very good technique for all materials, but it can be used for growing crystals for test conditions. You can grow large dimensions only in these two techniques, like the melt growth of Sokolsky or Bridgman. You can also try to get a large size in floating zone, but it is not possible to grow large size in flux growth. So this is another table which shows what are the techniques and what are the materials which can be adopted. For example, if there is more stars, like for example, if you have a semiconductor, you can use mostly pulling technique, and similarly for oxides and ceramics, you can use the pulling technique. Similarly, for zone melting, you can get good quality semiconductors. Like I've been telling, silicon crystals are grown using this floating zone in order to remove even oxygen trace amount of impurities. So there are some kind of comparisons. I will not go into the details for want of time. See, one of the important in material science, in particular in semiconductors, you might have heard a lot of information in the last 2 days, but these are the important measurement techniques. Mainly electrical measurements are very, very critical for understanding a semiconductor in terms of its electrical property. You all know resistivity is the basic phenomena or the basic requirement. If it is between 10 power minus 2 to 10 to the power 6, you call that material as define that material generally as a semiconductor. In some cases, that property will be slightly varying. For example, if it is a semiconductor with high insulating character, then the resistivity will be of the order of 10 to the power 7 or more at room temperature. Another important parameter which signifies the quality of a semiconductor is done by Hall measurement. In Nobel Prize, if you follow the Nobel Prizes given in physics, most of the Nobel Prizes have been given in the area of X-ray crystallography. And second, you may be surprised to understand, of course, astronomy and other areas have got many number of Nobel Prizes, but in particular with respect to fundamental science or material science, the Hall measurement itself has got more than 2-3 times Nobel Prizes. The quantum Hall effect and the related issues behind the Hall measurements have got a lot of Nobel Prizes. With a simple tool of having an electric current flowing through a semiconductor, while you can apply a magnetic field in the perpendicular direction or the normal direction, then in the other third dimension, you can measure the corresponding Hall voltage. With that measurement, you can find out what is the mobility and the carrier concentration, which not only gives you the quality of the material, but it also enables you to design the material for a given application. Uh, Similarly, there are other electrical measurement techniques like deep level transient spectroscopy, which can be used in order to understand defects which are present or impurities which are present inside the semiconductor, which are very, very critical in terms of materials like 3-phase compound semiconductors or 2-6 compound semiconductors. Photoluminescence is an optical characterization tool, which is also very, very important in terms of understanding quantum structures. And FTIR is another technique which is used to measure very low trace quantity of impurities inside these kind of semiconductors, only if they are optically active. X-ray diffraction is the basic fundamental tool, as you all know, in order to understand whether the material is crystalline or not. And the second important thing is, whenever you want to fabricate a device, the device is fabricated on a given orientation. You would have all done a basic understanding of solid state physics, where you are given a problem of Miller indices. Identifying the Miller indices, you also identify the crystal planes, and you do that on a paper. But when it comes to reality, you have to understand how to orient a material and then get the corresponding crystal plane. With that crystal plane, you can fabricate the devices, because there are various aspects of device fabrication. One such is what is called as the attachment energy, or the subsequent layers which are grown for device fabrication grows or is very good in a given orientation. And similarly, when the devices are fabricated on a circular disk of material or a wafer, then I showed you yesterday some squares which I defined as the areas of the devices. And the circular squares are kept inside a packaging system, which we call as an integrated circuit. Many of you use it in your computers. For that to happen, the materials have to be diced, and dicing can be done in a cleavage plane once the devices are fabricated inside on a given substrate. So understanding the orientation or the crystal planes is not just a 2-mark question in your MSc or any classroom work. It is so critical in terms of making devices. It is much more important when we want to fabricate what is called as a MEMS device. There is a device structure which is known as micro electromechanical switching device, which is used to pump blood inside the heart. You would have heard many people now have pacemakers, and these pacemakers work essentially by having a small device which opens and closes according to the flow requirement. And these devices are made essentially by understanding the proper orientation or the identification of the crystal planes. It is a process technology, but I don't want to go into the details. I just want to tell that fundamental physics is very, very important in various aspects of device fabrication. Strain calculation is also very important for, once again, device structuring. Crystalline behavior is another important thing when you want to understand various crystals for different applications. As I said, if you want to have a use of an anisotropic property, like in the case of calcite, which has a double refractive index, or the nonlinear optical materials, which has to be used for various wavelength up conversion or down conversion. So in those cases also, understanding the crystalline nature, the orientation are all very, very, very important. So there are also various complementary techniques. Generally, people use a scanning electron microscopy in order to understand the surface and then use its properties. So, for example, once a crystal in a cylindrical form is obtained, the diameter is generally, as I said, it is about 2 inches diameter when we started crystal growth in 1990. And then subsequently, it is with the orientation, the seed was oriented with 100 for very specific purposes. As I said, the attachment energy of the subsequent epi layers are very good if you use a 100 layer, and therefore the both ends are cut and then surface is oriented. And as I said, the primary and secondary flats are identified. This is the orientation of the primary flat is very important. Similarly, secondary flat is important for dicing the devices. The primary flat is important for alignment inside a mask where you put lithographic device patterns. So slicing is done after surface orientation. The edges are ground with respect to these kind of small variations in the diameter. And then lapping is done. It is double P, I'm sorry. The thickness is roughly about 350 or so. And then the thickness variation is less than 10 micron. And you also measure the bow, which is less than 25 micron. And it is etched in order to understand the defect density, or if there are subsurface damages. Polishing is also done down to this thickness. And then subsequently, the wafer is used for epitaxial process or for any other device fabrication. As I said, one of the fundamental technique which is used for understanding the properties of materials, in particular, let us say this indium phosphide, which is a compound 3-phase semiconductor. As I told you, the room temperature Hall effect measurement is the most important. And you can see here, if I have a tin or sulfur as the dopant, they will exhibit N-type characteristics. And we can have the carrier density in this range, or like 10 to the power 17. And typically, you get mobilities which vary with respect to the carrier density. If the carrier density is relatively high, generally the mobility is low, because sigma is equal to nu mu, and therefore the mobility will be less. if the carrier density is relatively high. Similarly, you can use p-type material like, for example, zinc, and then in this case the mobilities are very, very small. And one can also have additional double dopants, which I have done in my career, like cadmium and sulfur, which increases the mobility, and at the same time it can be helpful in order to have a certain environment for the device fabrication. So particularly the dislocation density is very low, because we have been able to lower the defect density by the use of cadmium, which is a p-type dopant. Sulfur, as I've told, is an n-type dopant, but in this case we have achieved a very good mobility, and we have lowered this so-called defect density by selectively having a low concentration of cadmium. Iron and chromium are used to have this kind of insulating behavior. Semiconductors, as I said, have a resistivity in the range of 10 power minus 2 to 10 to the power 6. But there are certain requirements, like, for example, if I have to remove parasitic capacitance in MOSFET devices, I should have a relatively high resistivity at room temperature. So that can be achieved either by what is called as intrinsic defect control, which is called as EL2, energy level 2. In the case of gallium arsenide, arsenic excess will produce this kind of defect levels, which are called as energy level 2 or EL2, and that can itself give rise to electrical resistivity of the order of 10 to the power 7. So there are various factors of growth parameters. The melt composition is one of the critical parameters, which can in turn affect the dislocation density. It will also affect the dip levels. As I told, if I have excess of arsenic, I can create a mid-level, which is known as EL2, and it can affect certainly the mobility, which is very, very critical for device fabrication. It will affect, or it will create what is called as a microprecipitate, and it will also
I think. Hello, sir.
Sir, you are muted. Sir, you are muted.
Muted,
You are
muted,
muted,
sir,
sir.
muted.
Sir, please
Sir,
unmute.
muted, sir. Kumar, sir.
now it's okay.
Now it's
okay,
okay,
sir.
sir.
Okay, sir.
Yeah, sometimes I don't know why it happens. Okay. So you are able to see the slide.
Yes, sir. Yes, sir. We are seeing, sir.
So these growth parameters like orientation, thermal gradient, dopant type itself, and the growth rate can all influence various properties of the materials. So one has to be very careful in understanding these growth parameters and the corresponding influence in their properties or in their defects. Because I'm from the crystal growth center, I just want to elaborate on the various importance of crystal growth issues. I can also tell you more about the recent advantages, but let us see how we are able to find time. So there are various materials which are being used as dopants, which means you can selectively take a particular element depending on the free carriers or the excess electron it will possess. For example, sulfur is the sixth group element. So in three-phase compound semiconductors, it will replace the arsenic, which is the fifth group element. So therefore, it will have one excess electron, and therefore it will create what is called as an N-type. And the distribution coefficient is in the range of 0.3 to 0.5. What we need is 1. But it's not so easy to achieve 1, but we can get something close to 1. That is how it is being done for most of the selected dopants. There are also other reasons to select a dopant, but if there is a second group element, for example, zinc, or let us say something like magnesium, then that will replace the third group element, or this indium, in which case you will have a divide of an electron. So this will be an acceptor type, or what we call it as a p-type. See here, beryllium has a segregation coefficient of 3, which means if you put beryllium as a p-type dopant, most of the top layer or the crystal, if you have a bowl of let's say something like 4 centimeters or 4 inches long, the top 2 centimeters or even 1 centimeter will have all this beryllium. That is why you have this segregation coefficient, which is very high. If it is very, very low, of the order of 0.08 or something, or 0.01, then in that case, the dopant will be mostly present at the bottom of the crystal. So one has to select a dopant which is close to 1 or very advantageous for a given application. Say, for example, if I takes germanium or silicon or even carbon, in some cases like tin, in these cases, you see, I have put N bar P, which means it is an amphoteric dopant. So this germanium or silicon can occupy both gallium or arsenic site or indium or phosphorus site. So naturally, it will either become N type or P type depending on the site occupancy. So one has to be very careful in order to select an given element in order to make it really N type or P type. Even in this case, you see, if I take silicon and use it as an N-type approach. But you see, if I use a quartz crucible, then it has 1 into 10 to the power minus 3 as a segregation coefficient, and 0.15 if I rotate the crucible very fast. Whereas if I take pyrolytic boron nitride, then it can have a segregation coefficient greater than 1, because this is not going to release any oxygen, and therefore most of the silicon will be very carefully distributed in the top layers of the ground crystal. See here, zinc, it is a p-type material and it has a segregation coefficient of 1. This is very, very important, because if it is having a segregation coefficient close to 1, the corresponding element which we have used as a dopant is going to get distributed very uniformly throughout the crystal, and this is also very, very important in terms of device fabrication. See, what are the ideal conditions for crystal pulling? The material should have a good melting point, or what is called as a congruent melting point. That means it should have only one unique melting point, and then it should have a relatively good thermal conductivity, because there are conditions of the heat transfer, and the heat transfer can be happening through radiation, convection, and mainly through conduction. So that is the reason why we need a good thermal conductivity with respect to the material we want to crystallize. It should have a low vapor pressure so that the material doesn't have variations in the so-called stoichiometry or the composition. It should have a low viscosity so that the material, if it is too viscous, it will be very difficult to grow it as a single crystal. Suitable growth aptitude is also necessary in order to grow it along a given crystal orientation, because as I told you time and again, the orientations are very, very important in device fabrication, because it is not only one layer as N-type layer or P-type layer or N-type crystal or P-type crystal we are going to use it for devices. We need a NPN junction or PNP junction or PIN junction or simply a PN junction in order to fabricate a device. So there are some important conditions I have listed here. So once again, the essentials for pulling are, we need a good crucible which can be supporting the material without reactions, and then the means to heat and control, a seed crystal and a way to hold it, and a mechanism to raise and lower this seed crystal. This is another important thing of the crystal growth process. As you can see, we need to raise the temperature in some cases up to a temperature of 3500 degrees centigrade. Normally, we can go up to 1500 degrees centigrade, or in the range something like 1000 to 1500 degrees centigrade, depending on the type of material. And you see, resistance heating one can achieve through carbon as a heating element up to 3500 degrees centigrade. And the advantage is it is very simple and versatile. You can use various heating elements like nichrome wire and other heating elements which are used in your iron boxes. There is a company famously by name Kanthal. Kanthal produces various types of heating elements for resistive heating applications. There are many specialized heating element is known as molybdenum disulfide, which is very good to use even at open air environment. Otherwise, you know, molybdenum itself will oxidize if you use it above 550 degrees centigrade in normal air conditions. So you prepare this Kanthal as a heating element, And this is one of the famous company worldwide which produces heating elements alone for various applications. One can use platinum wire, iridium wire, or alloys of this in order to produce good quality resistance heating. You can also use tungsten wire or tungsten sheet, which is what we are now using for growing alumina crystals. We can use induction heating, as I said, and we can use various other types of heating also. One of the important thing is for most of these heating elements, we need a good container, whereas for arc image, we don't need a container, which is done, for example, for materials like zirconium oxide or magnesium oxide. So these are some of the common crucibles, as I told, platinum, iridium, molybdenum, tungsten, carbon, silica, all can be operated within these temperature ranges, alumina, for example, and their melting point is also given here. But we have to also understand the type of environment with which you can use platinum or iridium. Generally, iridium is not used comfortably for RF heating, but otherwise you can use it for mostly resistance and RF heating, all these metallic materials in terms of a container and the type of heating. Whereas silica can only be used for resistive heating. You cannot use silica crucibles for RF heating because RF has to have a kind of clubbing or it should receive these frequencies, and therefore silica cannot receive it, and so it cannot be used. You can use simple glasses. We all use on a day-to-day basis various glass materials. So for example, you can use for silica, which is a glass, and that's how it is mentioned here as silicon, and it can go up to 1350. Pyrex is one of the normal glass which you use on a day-to-day lab applications. So you can grow materials of nitrates, phosphates up to 500 degrees centigrade. Even plastics can be used like PTT, nylon, polythene, depending on the temperature range and depending on the material you want. For example, you cannot take a HF in a glass like Pyrex or any glass for that matter. HF may be a good solvent, but you cannot use it because it will corrode the container very easily. So similarly, you can use nickel crucibles for fluorides, calcium fluoride and other fluorides. Cesium fluoride is used in nuclear physics as a radiation detector. And for this purpose, nickel crucible or copper crucible is most suited. Similarly, you can use for organics, sodium, potassium based materials, even stainless steel metal crucibles. You can use platinum for mostly alkali metals, nitrates, halides, as I said, cesium fluoride, etc. Now I stop more or less this talk up to the crystal growth aspect. Now I shift to another domain of the fundamentals of semiconductors for another 10 to 15 minutes, and then I will stop to get you feedback. So I have written a book on the local vernacular language, which is Tamil. I encourage all the youngsters here to attempt, at least at your level, wherever it is possible, to write an article in the language of your vernacular abilities and then publish it, so that school children or students who are not so familiar with English are able to get a pickup on these areas. So this is a small attempt. I have written this book on electronics, photonics, and spintronics in my language, which is the vernacular language. So basically, what is it? It is all about atoms. So in a given atom, you have the nucleus, you have the proton, you have the electron. These are all fundamentals which are all familiar. And these relative sizes are very, very important. A human is about, let's say, a couple of meters, whereas the electron orbital is about 10 to the power minus 11 or less than a angstrom. An atom is of the order of angstroms, and we have typical dimensions of any aspects of materials or human systems around us. Now I want to tell you one important thing. Many times we are told about semiconductors by drawing two lines. one line is given out as a bottom line, which is called as a valence band, and a top line, which is given out as conduction band. And there is a gap between these two, which is called as band gap. And you are told that this is a semiconductor. Actually, the line is only a representation, a straight line. It should be drawn as a wave only. So please understand, this line happens to come like this, or a line on the top, which is the conduction band line. These two lines are not actually lines, but they are a representation of this wave pattern. Why or how this wave pattern occurs is because you have an electron on one atom, outermost orbit. You have another electron on the outermost orbit of the adjacent atom. So this electron is being pulled, or it is being repelled by this electron, neighboring electron, and that is why this electron tries to get attracted in the wave pattern, and then it keeps moving on a notional way. Why can't it be pulled in a straight line way? Why should it go this way or with a wave pattern? Is because essentially because there is always an electric field surrounding this and surrounding this, and hence accordingly the electron, which has a mass, is subjected to the electric field surrounding the electron here, and similarly the electric field surrounding this electron has an impact on the electron at the neighbor. And due to this, we all remember electromagnetic waves, how it is created, and therefore the electric field surrounding the electron is being is altering the wave, is altering the nature of movement into not a straight line but as a wave. Most importantly, we should understand, I have drawn some patterns to make you understand, it is not exactly moving like this perfect pattern. It can move in this way, which has an amplitude which is more in some place, which is less in another place, because we don't have electrons only in a straight line fashion. We have electrons above this given atom, below this given atom, in a diagonal place, and in a close by place, etc. And accordingly, this so-called pattern may varies, and Professor Thangavel can explain to you in a very detailed way. He has done a lot of work on the theoretical aspects of this band theory of solids, wherein he will show you how this wave pattern or this corresponding nature of these waves happens with respect to the positional state of the electron. Now, I want to tell you one important thing using this representation. Many times you would be puzzled to know if a material is like silicon and another material is germanium. Both are in the same periodic table and they are literally adjacent to one another in the periodic table. So why one material has a different mobility compared to the other element? It could be a curious question. The reason is not all these atoms have the same distances when they are adjacent to one another. Even though they follow the same crystal structure, their distances of adjacent atoms are slightly varying, and accordingly this nature of this wave or this so-called band varies. And therefore the electron which moves through this, or let us say the electron which moves through this wave, will have a different let us say momentum as it travels along this crest, and then when it falls back it will have a different momentum. So when they vary the momentum, there are only two possibilities. One, the electron should keep on moving with a very high velocity. It should shoot out of this point here, whereas it is literally not possible, and it is not possible because of the conservation of momentum principle, and therefore this has to fall down, and when it reaches this maximum, the mass of the electron varies, and therefore that is called as an effective mass, and that effective mass contributes to the variation in the mobility for different materials. So even though the materials or the elements are adjacent to one another in respect to the periodic table, the nature of the distance of separation between two adjacent atoms and the crystal structure of a given material accounts for the variation in the effective mass, and because of the variation in the effective mass, the mobility of different materials are very different. So you please understand this first principle as to why the mobilities are very different with respect to two different materials. Then I told you, if we have not a flat line, which is usually done in most of our undergraduates or even in postgraduate, we are told this is a line which is valence band, this is the line which is conduction band.
Sir, sorry to disturb you, sir.
Yes.
Sir, the slides are not matching with your talk.
Yeah, it is not to be matching, but if you can see the slide, I'm only trying to explain as to what is happening. Are you able to see the slide?
Yes,
The
sir.
slide
Yes, sir. The same
put,
slide. Same
is
slide.
constant and band gap.
Yeah?
The slide is on lattice constant versus band gap.
Yeah, that's not very important. Okay. I'm
Okay,
not
sir. Okay.
showing anything
No,
with respect to the
sir
lattice.
is speaking
No,
is
I just
overall this band gap, all the 3-5 semiconductor and as well as 2-6
Yeah,
semiconductor.
you can
Overall
see
speech
like
is
this.
speaking.
Okay, Thangoil, I will explain. Can you see this slide now? Are you able to see this slide?
yes, sir.
Hello?
Yes, sir.
This is a classification of materials. This is how most of the times in your undergraduate or in your school level they are taught. So you have a line, and if this line is a straight line like this, we are told which is the energy, and you can be simply shown that this is a valence band, this is a conduction band. I'm trying to tell you that the valence band is not a line, or a conduction band is not a line. It is a representation of this so-called wave pattern. Do you follow this? Are you okay now?
Yes, sir. Yes, sir. Yes, sir. Very
No,
true.
somebody is questioning me, so I want to make him follow what I'm saying. This slide is not matching is his worry. I'm saying you don't worry about this slide. You only follow the way I'm trying to explain. So here you see the energy versus wave vector, and this line is a curved line. I have explained to you why it is like a wave. And what is this conduction band? You can understand this pattern because I told you there is an electron.
Sir, I think mute, sir. Kumar, sir. Mute is coming, sir.
Okay, now it should be all right.
Yes, sir.
So this valence band you can easily follow. What is this conduction band? Why is it now happening? Because when we apply an electric field or supply some form of an energy, this electron, which is on the valence band, has to raise to a higher level, and this has to be not on the same line of this valence band. It should be slightly above this valence band. And in order to distinguish this line with respect to the raised line, we make it as an inverted line or an inverted wave, and this is what we define as a conduction band. Now it's perhaps easy for you to follow that the distance of separation is what is called as a forbidden gap, and this forbidden gap defines the band energy, and this band energy is very, very important in understanding any material, either it is a conductor or an insulator or a semiconductor. So if it is a metal, the Fermi energy overlaps, and therefore there is no real gap, whereas in a semiconductor there is a defined gap, whereas in an insulator there is a very large gap, and therefore unless you apply a very large electric field or very high temperature. Yes, somebody wants to talk?
Sir, no problem, sir. You can continue, sir.
Okay, so these are now
Sir, just
the
one question. The lattice constant that you are saying, is it K?
I'm
Momentum?
not talking about the lattice constant at all. I'm only trying to make you understand that there is an atom at this point in the valence band, another atom adjacent atom at this point, and they are having their electrons in the outermost orbit. This atom at this point also has an electron in the outermost orbit. This electron can either be attracted or it can get repelled. That's what I am trying to say. The lattice point
Oh,
is
yes, sir.
not important at this point.
Okay, sir. Okay.
Sir is giving the overall the band structure regarding semiconductor based on this work. The conduction band and
Yes, sir.
valence band,
Yes,
how
sir.
the
Yes, sir.
density of state is moving, like that.
Yes, sir. Thank you.
Okay. So I think I will quickly move on to some materials instead of trying to give you fundamentals. So there are various reasons for selection of devices. You need a sensor, you need an RF device, you need an light emitting diode, you need a PLD, programmable logical device, memory device, system on chip, which comprises many devices into one area. So, for example, each of these materials are falling into various segments of the previous slide. Let us say gallium arsenide, it can produce RF amplifier and microwave devices. Gallium nitride is a wide bandgap semiconductor with a high breakdown voltage and relatively high mobility. So it can be used in power electronics, it can be used as LEDs, and also in RF applications. As I told, it can be used for high frequency and high temperature operations. Silicon carbide is another powerful material used in power electronics, particularly in e-vehicles nowadays. Organic light emitting diodes are also parallelly in production. Initially, they had a very small lifetime. Now, Samsung and related companies have made significant advances in the lifetime measurements, and therefore they are able to produce devices which can have more than 5,000 hours. That's how most of the Samsung mobile phones use organic light emitting diode materials. And organic photovoltaics is another important area because you can use relatively cheaper materials in order to produce solar cells. And these solar cells can be, or rather these organic materials can be coated on any corrugated surface. And so even on curtain, it can be coated, and therefore you can get relatively small efficiency, but it is enough to have a cheaper material. I told you something about the micro electromechanical switching device, which is used in healthcare. It is also used in automotive. It can also measure very small variations in pressure. And so in the design of aircrafts and air systems, this is being used nowadays. There is also a counterpart to this. Instead of electrical signal, one can also apply optical signal, which can be called as some ohms, micro-optical optomechanical switching devices. There are a lot of function-based segmentation in digital logic, etc. I'm not going into the details, but I want to make some understanding of these device segments so that you will follow one particular area of this device segment, which is LEDs. By and large, I worked very much on LED material structures, so I will try to highlight some aspects of these LED structures. One of the important things in materials, particularly in these solar cells, is that instead of having one simple material like silicon or gallium arsenide, you can tune the band gap with variations in the band energy by putting layers of materials with a different band gap, like EG1 with as a particular band gap value, like in this area, which is close to, let's say, something like less than 1.5 or 1.6. And then as you go here, you see this area, the red spectrum is covered. So this band gap energy is EG4, which is very small compared to the first layer. So this first layer will absorb the high intense solar radiation. The second layer will absorb lesser intense radiations, and correspondingly weaker intense like infrared radiation is absorbed here. So all these things can be in some form clubbed, which is called as tandem solar cells. And this, in theoretical terms, can produce an efficiency close to 87%. Though it is not practical, but people have shown in space applications, these tandem cells can produce something close to 52% efficiency. These are some of the relatively standards which are being used in current segments of solar panels used for terrestrial applications. As you can see, this is a solar system we call. Everything, each one of them is called as a panel. And if you consider this entire thing, it is called as a system. So this is a system, and each of these panels have produced something close to 540 watt peak. About 15 years ago, the maximum energy which was produced by a panel was only close to 110 or 120 watts. Now we cannot produce, or most of them very standard is about 540 or around that energy. This is a house in Kerala. This is a self-sustained energy production. There are also interesting things happening. A person in a village in Haryana has mounted the solar panels on a cart pulled by bullocks, and then he takes it to the farm and provides the power wherever it is needed. Similarly, the panels are now mounted on water bodies, and they can produce good quality power also. There is a standard in terms of these solar cell efficiencies by NREL. This is an internationally recognized agency in Colorado in the US. And so you can see, for example, these are the purple color is called as 3-5 multi-junction solar cells. As I said, it is a tandem solar cell. So this is close to 50% efficiency, which is used in space applications. Whereas if you see the terrestrial applications, which is around 20% efficiency, silicon, for example, this blue color, this is the silicon, which started somewhere in 75s, and then it reached an efficiency close to something like 18 to 20% by 95, and it is almost the same. Still, many of us use silicon cells for many of our terrestrial applications. Only thing is, we have been able to increase the amount of power being produced in a single panel, and that is what is very important as of today in silicon cells. Whereas you, by and large, because there are a lot of youngsters here, you must realize.
Sir, excuse me, sir.
Yes.
Sir, slide move out, sir. Slide is not moving. We can't able to see the slide, sir.
One second. Now are you seeing?
Sir, we are seeing only the plot between lattice constant and band gap, sir. On the slide, Nikki the way.
Okay.
Same slide, I think.
No, wait a minute. Are you able to see the house with the panels? Are you able to see NREL?
Yes, sir. Yes, sir.
Yes, sir. No slide changes, sir.
Okay. So you see here, this is the solar cell for space applications with an efficiency of the order of 50%. And as I told you, silicon cells are around 20% efficiency. Cell efficiency, system efficiency will be 1 to 2% lower. But as there are many youngsters here, I want to tell you, you don't worry about even 20% or 50%. There are still in 2010, groups started working with an efficiency less than 4% or 2%. These are now very seriously work. Many research groups are working, and you see here they have been able to achieve something close to 18%, which is close to 20% of silicon over something like 50 years of silicon. Within about some 10 years, they have been able to achieve the efficiency of silicon. These are very, very important cells, which are known as the cells which are based on what is called as the perovskite cells or perovskite crystal structure cells. So these are linked with organic materials, and so these perovskite cells are now very seriously being followed up by many research groups in order to achieve relatively good efficiency of the order of silicon. The reason is perovskite cells, as you see here, are important, which is the plot here, because they can be grown or realized at a relatively normal price, and they can be realized as thin films without much loss of materials. So there are a lot of other informations on various materials aspect. I'm not going into the details. I just want to touch upon one particular aspect of today's materials world, which I told you yesterday, topology. Topology is the study of continuity and connectivity. If you take a small thread or wire, and then if you close these wire ends, it can form a circle, or it can form an ellipse, or you can even twist it and see a pattern like this. I hope you are able to see this. This is the topology related surface states. So as I told you in the last day's lecture, this is a topological insulator. The Fermi level falls within the bulk band gap. So here you see the Fermi level falls within the bulk band gap.
Sir,
Yes.
they're not moving, sir. The slide not moving, sir.
Now, are you seeing?
No, sir, not changing.
Okay.
Now still the solar panel only available, sir.
Okay. I don't know what is happening. Suddenly there is this problem. Now,
No,
are
sir.
you seeing some spintronics?
Yes, sir, available, sir.
Now. Yes.
Okay. So this is the topology. So if I take a small thread and then close the end of the thread, I can make a circle or an ellipse, or I can make a pattern like this. So if you make some mathematical patterns, or if there are some conducting surface states like the patterns which I showed in the previous slide, then the bulk of the material will be insulating, whereas the surface states will be conducting. This is a topological material. I cannot go into the detail for want of time. But topology is developed as a field of study out of geometry, set theory, and analysis concepts such as space, dimension, transformation. So it's a little interesting area. Many of you who are youngsters, I wish you follow this and then try to understand the importance of topological materials. I don't want to go into various details, but if you have a vacuum fluctuation on either sides of two sandwich type of area, then the intermediary area, which is called as a Kashmiri plate, even with a separation of 10 nanometer, you can realize about 100 times the typical size of an atom is what we call as 10 nanometer, the Kashmiri effect, which is equivalent to 1 atmosphere of pressure in this area here. So these are very interesting issues behind topological materials. Due to want of time, I cannot go into the details. So a topology is nothing but a donut, which is what I see here, can be transferred into a coffee mug, and these are two different things. But as you see here, this has what is called as a genus, which is given by a number 1, and this is also a genus which is given by number 1. This is what you have to understand as genus, and this is all done by Euler. Except for Euler in physics, nobody has understood or explained nicely about the time phenomena. So you can follow this in general physics and try to understand this. I'm not going into every aspect of this expression, but one thing is the quantum Hall effect can only explain to you the presence of these surface states in terms of the fractional quantum Hall effect, and that in turn can create patterns like this. And if you can
Sir,
see
change the
this
slide, sir. Please, sir. Change the slide. Next slide. Next. Yes, sir. Yes, sir. Yes, sir.
you are seeing,
Yeah, yes, sir. Yes, sir. We are seeing, sir.
okay, you are seeing this slide.
Yes, sir. Quantum Hall effect, sir.
Okay. So this is defined by what is known as a Chern's number, and these are known as Berry space. I'm just giving you some names, throwing some names. If you are interested, you can understand it in detail. So basically, the topological, the distinction between a conventional insulator and a quantum so-called spin Hall insulator is this. So you can have a trivial state And this trivial state can be combined with this kind of Fermi states, and this can also be represented with respect to k wave vector equivalent to 0 or pi. You have to understand in detail this quantum spin Hall insulator, then only you will understand this. But I just want to make some representative understanding of this. In current world, the material science is moving from a normal understanding of materials based on the selective properties of materials to machine learning and artificial intelligence in order to select materials of your interest from a group of materials which are already available. So data analysis can be done, machine learning can be done, and then subsequently you can classify a group of material based on its structure and other properties, and then classify the material into that particular group, and then you can select the material of your interest based on this artificial intelligence or machine learning. So I just stop here, and if you have any specific question, I'll be able to answer them. Though I have not very carefully discussed everything, but I can quickly answer or show some of the slides once again if it is of any relevance to you. Hello.
Sir, talk is very good talk, sir. Is semiconductor material and devices, sir. I think we now talk open for discussion. Any members, faculty members and students? Sir, given more informative overall overview of semiconductor technology, what are the materials we are using in the current technology? That is overview talk, and as well as sir has given little background of theoretical knowledge also. I hope everybody is available. Yes, Dr. Parani. Hello.
Yes, Tangal, yes, Tangal, I am here.
Yes,
I am
yes.
here.
Please, any
I'm
query
watching.
regarding
I'm
sir?
watching. No, Tangal,
Okay.
no.
Okay. Any other questions from the audience?
Maybe I was too fast because of
It's not
some
fast,
other-
sir. It's good, sir.
No problem. Yeah, no problem. But
It's,
I,
we know that, sir. No problem. It's not
yeah,
fast, not
I
slow.
explained the fundamentals of semiconductors.
Yes, sir. Yes, sir.
Hello.
That is
Hello. Good evening,
Yes,
sir.
yes. Yeah, good evening.
Yeah, sir. I mean, I'm very indebted to you for this kind of presentation. It's really informative. I have one query regarding the solar cell. Silicon solar cells are doing quite a far better job than other kind of other generation of solar cells. And particularly perovskites are, see, this kind of industry is booming. I mean, research is booming, and trying to achieve the efficiency of silicon solar cell. But these perovskites are also having a problem of this lead kind of materials, lead or cesium kind of materials.
Perovskite need not have lead, okay? Because basically perovskite is a crystal structure. It is nothing but a barium titanate crystal structure. So there is no need to have lead in that or
That is
cesium in that.
yeah.
But
the one
all
which
started with
has achieved the 20% efficiency, that is, I think, this
yes,
that
you
is
are
a
right.
lead based.
Yes, you are right. But you know, there are several materials, including your so-called thermal power plants, which are more harmful to humankind than many other reactors like a nuclear reactor. We are not told in depth about the various problems in various environments. But you must realize that the thermal reactors are so-called thermonuclear or thermal reactor power reactors produces lot of waste or dust which can be very dangerous to human health. but we are using it because it is more efficient and it is considered to be relatively less toxic compared to an explosion in a nuclear reactor. Likewise, we are not going to consume lead directly in a solar panel. It is only a process which is used to make the solar panels. Once a solar panel is made, we are not going to extract any lead from there and then use it, or you are not going to touch and then use that lead for your
So, but that
day-to-day.
waste, but that waste disposal is also a concern regarding, I mean, if lead is
Yes,
used
yes.
for that.
No, I do understand and I really accept your views that there are several harmful effects of science and technology. But there is always a balance which we have to strike, and we have to balance the strike in such a way what are the gains and how to later on minimize the toxicness of that kind of an environment. So, as I said, lead-based perovskites are currently used, but people are working with different materials. I don't want to tell you the exact elements being used. People are working on different elements which are rare earth based also. And in that case, naturally, we'll get a very good efficiency and we'll be able to move on uh, by minimizing the use of lead-based material. Lead is used in our day-to-day applications for various activities. So it is not toxic unless it is, also, for example, I'm showing you a slide which is with gallium arsenide, aluminum arsenide, etc. Arsenic, as many of us know, it's one of the dangerous toxic material. But it is used very commonly in your chocolates. Do you know this?
Even I had worked on CDS, cadmium sulfide, which is also a very good active material for the solar cell, window material for the solar cell. But it is always a concern for using cadmium.
Yes.
Even
See,
we
a
are not
researcher
using
should not
cadmium.
worry about, no. A researcher should be cautious about your so-called layman, but you should not worry too much about all these aspects. You should realize that the advantages are there and how to minimize the disadvantages or harmful effects. As I said, arsenic is used in all your chocolates. It is used as arsenic dioxide, arsenic trioxide. And so it is not at all harmful. That is the reason we are consuming so much of chocolate.
One more thing, sir. What about this silicon nanocrystals if they are used for solar cell? Because they could be more efficient, I mean, as compared to polycrystalline or amorphous solar cell. Amorphous
I
silicon.
didn't have much of the time. There are various aspects of these solar cells. And as you rightly said, silicon nanocrystal has been used by EPFL Switzerland. My student only worked on that and he is running a company. He is actually manufacturing the nanocrystalline based solar panels in Tamil Nadu itself. Nanocrystalline silicon. Okay. There are two problems in this. The nanocrystalline silicon has still a surface coverage which is relatively less when compared to a simple single crystalline silicon. And the formation mechanisms and other things has certain limitations. So the efficiency is only about 6%. But the claim is the cost factor is only about $0.6 way back in 2000 itself. At that time, the single crystal silicon was costing about $1.5, $1.6 per watt. Okay. So the problem was the nanocrystalline silicon, the efficiency is less. But in current days technology, we want more power, like 540 peak I showed you. You cannot go and buy, in my house itself, I have 4 solar panels, or so 4 solar systems. The first one I bought about 20 years ago was only with 160 watt. That's 160 watt panel I cannot buy now, so I have to totally replace it with a new system which has output of more than 500 watt. So you understand the technology is evolving and therefore it is not so easy to have relatively low output. So this nanocrystalline silicon based solar panels have less power, but they are in very huge demand where the weight and other issues are of very great importance, because that can be coated on glass surfaces and relatively it can be produced on very easy substrates also. It doesn't need a crystalline substrate, which is relatively heavy, and the fabrication process is little complicated. So people still work on this nanocrystalline silicon or nano material based silicon, and then they produce power for very small domain applications. But if you want it for large system application, large power demand applications, then they are currently using copper indium disulfide or CAS cells. First Solar is a company which is producing copper indium disulfide, as you might be knowing very well because you have worked on cadmium sulfide. Cadmium telluride based substrates are used for CAS cells, and they produce very high current, which is very much useful when you have a huge demand during the daytime. If I am running a printing press, and if the printing press is in huge demand of a very high current, then in that case, instead of depending on the town supply, I can depend on the solar panel output, because it produces very high current. Short circuit current is very high in this 2,6 based solar cells, and that is very important. So depending on the application, you have to use this. And if you have only silicon, then it can be used as a concentrated solar cell. I have some slides also, but I don't have the time to show it. For example, you can have 1,000 suns focused on a small 1 centimeter square cross section of indium gallium arsenide, and then you can produce a very high output of the so-called solar output. That way, you can get very good efficiency also. These are some ways to modify technology, and there are also other parallel technology progresses being made. Where, for example, there is what is called as a PERC cell, which is being currently used everywhere. We are using N-type silicon in PERC cells, whereas if you use P-type silicon, this is called a stopcon, in which case you can have the backlighting also in the solar panel. You all know a typical solar panel is looking like this. I will show for this interest of others. You may be knowing very well about all this, but for people who are sitting here, I want to show some slides of these solar panels.
Yeah, thank you, sir.
No, you can, if you are not interested, you can go. I want to show something for the sake of those who are sitting here. Okay. See, I don't know if you see this slide. Are you seeing this?
Sir, we are not seeing, sir.
This one, are you seeing?
No, machine learning only showing, sir. Machine learning only.
Oh, 1 minute. I'll show you.
I think it's
Just
changing other slides.
Yeah, one second. I'll show
Maybe some other PPT, sir.
you. Yeah. You see this?
Yes, sir.
Yes, sir.
120,
Okay, this,
422,
yeah, this is
422.
called as, yes. This is called as concentrated solar cell, 36 indium gallium phosphide layers on top of indium gallium arsenide as the alternating layer on germanium material. See, this small area is a typical cell. And this is the Fresnel lens, which is used in your earlier power projectors. And this can focus on this cell about 1,000 suns. And this can produce very high efficiencies in a very small area. So if you have a solar panel with all these solar panels, this is how a typical solar panel looks. if you have a solar panel which is typically like 6 feet by 3 feet, in this, if you use these concentrated solar cells, you can use only about 2 feet by 1 feet. So there are various ways to improve the efficiency or improve the power output, depending on where you want to focus or how you want to focus. So on the question you raised on nanocrystalline silicon, it is still being produced, but it has a very small domain application as of today, because these concentrated solar cell, PERC cell, TOPCon cell have all come in a large, in a big way, and therefore the requirement of nanomaterials or nanocrystalline material of silicon is getting reduced, if not totally eliminated. Okay. You should not get discouraged, but it can still be used for a very specific application. Okay.
Okay, sir. Thank you, sir.
I
Thank
think
you.
any other questions from audience?
Okay. I think I will
Uh,
stop.
I think everybody's
Tired.
all
It
the
is already
students and
late.
faculty members. Anyone have any doubts? Sir, I have one question, sir, from Kumar sir.
Yes, yes, please.
Yeah, sir, I see nowadays the quantum material and devices, people are working in
Yes.
the directions.
Yes.
How will the feasibility in the quantum computing scenario, in the current scenario, the existing classical computer to quantum computers?
See, classical computers will continue to work for various applications. As I said, in solar panels, you have various advantages in different segments, like concentrated solar cell, but they have only in certain areas the applications are being considered. Similarly, quantum computation has still a lot of unsolved problems. Very recently, only Google has been able to address one of the critical problems. So very soon we'll have quantum computers. But these quantum computers will be high-performing computers like your supercomputers, which will not come to the desktop kind of situations. It will be more towards storing information and retrieving information for large volume of data, and then for processing this information for a very secluded way of information. For example, I don't know if there are technical things which I can't disclose, but you must understand there
Yes,
are
sir.
some countries which are not happy to give the process technology to other countries. They are willing to sell the device, but they are not willing to manufacture the device in a given country. The reason is they can impregnate their own ideas into the device process, and they will follow the device performance wherever it is. That will not
Yes, sir.
happen when you have a quantum computer.
Yes,
Okay.
sir. Yes, sir. Thank you, sir. Thank you very much, sir. I hope,
Okay.
I think everybody's enjoy the Kumar sir talk. Sir talk is more informative and current existing knowledges. I
Thanks.
thank Professor Kumar sir. It's a very excellent talk. Is very. We will meet again soon, sir. Thank you, sir.
Thank you. Thank you.
Thank you very much, sir.
Thank you.
Thanks, Dr. Saravanan.
Yeah, yes, sir.
Thank you,
Thank you, sir. Congratulations, sir.
Thank you.